Thank you for the nice words, Ignacio, and very nice to see you all. So now today I will tell you about rotor aerodynamics for wind turbines, and that's because that is what I'm doing in my research, and that's also, you can say, it was the title in the announcement for this professorship. So I felt it was natural to do it like this. So when I should prepare this presentation today, I have had some thoughts about why am I actually in research, and it came up with 4 different points for this. It is, you can say, fascination. It starts out with the fascination of you can say equations. It started out actually in high school, where I realized it's hard to predict the future, but it's actually, equations can actually do it, because now I've just taken this equation up here that says what the power is equal to. 300 years ago, when you put up a wind turbine, we wouldn't know how it would actually behave, because we didn't know how things were related. Now we know, okay, if I put up a wind turbine, I know it depends on the radius of the rotor. It's something with the wind speed cubed and so on. So that's fascinating that we can actually describe the world with mathematics. Another thing is creativity, that we can make our own investigations and discoveries and analyze the things, and then realize, okay, this power coefficient up here, it can actually be described this way. I won't bother you with this otherwise, but it's also fascinating that you can realize how things are connected. And then I really like the collaboration. I need to have fun when I go to work, and I enjoy that 1 + 1 actually sometimes are greater than 2, because when you work together, you actually get better results than working 2 single persons in parallel. And then purpose, that's super important for me. It is important for me to use my knowledge for a greater cause. I can tell you that I was, before I came into research, I was an engineer in a consultancy company working with oil. I had great colleagues. It was interesting what I did, but I kind of missed, you can say, the greater cause. I couldn't see a way forward. So that was why I had to change. So purpose is super important for me. And that is now bringing me to purpose, because some of you might know that I really like to consider stuff and analyze stuff on the back of an envelope. So that is what I'm dragging you through now. So forgive me for that. We have the globe. It has a radius of more than 6,000 kilometers. We have an area on the globe that is more than 500 square kilometers. We actually became more than 8 billion persons at the globe a week ago. So we have, each of us, a bit more than 60,000 square meters per person. What is 60,000 square meters? What is this? Well, that can be inside Tivoli Garden. So the red line shows the Tivoli Garden, and then we have this red rectangular that is then showing this 60,000 square meters. And if we then say 70% of this is water, a third of the land is desert, then we have left 12,800 square meters, or 1.8 times a soccer field where we can live. That's how it is. And this area won't become bigger because we will be more people. And you can also find out how much air are above us. Yeah, we have 8.4 kilometers of air if it is at the same density. So we have this straw we live in, 8.4 kilometers high, and then an area of 60,000 square meters. And if we then take a look at the CO2, then we know right now we have 460 ppm. We let out 7.5 tons CO2 per year in Denmark. And that is then an increase of 2.7% in 2021. And then a Dane will actually then increase the CO2 with 11 ppm per year. Globally, it's 2.4 ppm. So to put it kind of directly, we float in the ruthless universe on our 1.8 soccer fields. we have one person here, we have to get food from this area, we have to let out the garbage and so on. So we just have to organize our life in a sustainable way. That's my point. Enough of purpose. Now I want to tell you about aerodynamics. So I will tell you about the background for my research, and then I will give you selected examples because, yeah, I could probably tell you something for hours, but I have to limit myself. I will tell you about airfoil performance and design, about rotor performance and design, and then of course the polar Rotor, and something about teaching and projects and my vision. So the background for my research is that I arrived at RISU back in '97 to a very well-functioning group of persons led by Flemming, together with Kenneth and Gunnar and Per Vølund and Helge and Niels and Jørgen Tirstrup and Bjørn Fuglsang and more. At that time, we had tests of the Nibe turbines. We had a great collaboration between many institutes, as Ignacio also told. This is old, this is back in the 80s. And here we can see the Tellus turbine instrumented with instruments that was quite advanced for the time also. And here we can see some results where we have forces up here and then angles of attack out here. You can see how the forces changed with the radius. That was new at that time. So for me, it was an excellent start. I started on super solid shoulders. So this is where I then continued the work from this together with many persons. I will now give you some selected examples. Start out with airfoil performance and design. So here you can see Inaugural. They made this test of a 10-meter diameter rotor, put in the world's biggest wind tunnel. A lot of people had to do this together at Inaugural. So they made this excellent data set, and then I analyzed this. Then I took pressure measurements from 5 different sections on this blade and tested it. Not tested it, I analyzed it and realized that this, this black curve was something tested in the wind tunnel, this lift curve. But if we then analyzed at the tip, then we had the red curve. And if we analyzed at the root, then we had the blue curve up here. So it turned out that even though we tested in the wind tunnel, it was not so easy to know what should actually be, how we should describe the forces on the turbine. So then this 3D correction is about taking what is in the wind tunnel and then correct it for the forces. And because there are some centrifugal forces running out the blades, you can see the streamlines over here. And then I made this model. And I tested it against another turbine. This is an active stall regulated turbine. And you can see if I just use the tunnel directly from the wind tunnel, I would have this pink curve, the lower one, not really very close to the gray one. But then I made the red one, and that was okay. And actually Takis and Martin, they made the blue one, so they also did well with their model. So there was a lot of attempts in trying to make these 3D corrections. And at that time, it was very, very important because turbines were stall regulated, a lot of them at least. Now it's less important, but still important. So this was, you could say, a huge area back in the end of 90s and during the 90s. Then airfoil design was also very important because wind turbines, they used a lot airfoils from the airplanes. And they didn't really have the right specifications because they were made for takeoff and landing and so on. So we designed different airfoils. We started actually out with the RISU B1. There were more before this, but I was not involved in more than this was the first one that I really was involved in, this RISU B1. Then I came to the RISU C2 airfoil, and later also this light rotor project airfoil. So this was again in the collaboration with researchers, and during this phase, we realized what was needed for wind turbine airfoils. So when we just run in this area where we run in normal operation, we need the airfoils to be very efficient aerodynamically. And this, you can say, and that's the aerodynamics. But then you also have to take care of the loads, and this has something to do with the maximum lift. Should it be high or should it be low? You also have to make it reliable, so we have to put the transition point in the right place, the transition from laminar to turbulent flow. We have to ensure something about post-stall, how is it actually separating out there? And then for sure, we have to make design for high compatibilities and design for high stiffness. So this was something we learned during this process of designing the airfoils. And we tested the airfoils, and here you can see B1 and C2 airfoil tested, and they are very similar. You can say C2 is kind of an update of B1, so we have actually a slightly more efficient airfoil in the C2 airfoils. But what we also did was to license these airfoils. So we licensed it to many airfoil or wind turbine manufacturers, and they have used it in their megawatt designs. And I could read them, and I don't say where this goes, because that is not what those licensing the airfoils want to let us do. But I could read in Wind Power Monthly that these airfoils were actually used in the 10 megawatts Vestas V164 turbine, and this is actually, you can say, the ultimate test of our research, that we can actually go out with our research and let the industry use it and move forward and make things better. So that's, you can say, ultimate test of the quality. And of course, I'm also super honored that they actually dared to use these airfoils. So that's super nice. Rotor performance and design, I also have worked a lot in. So I want to tell about the dynamic test that Ignacio also mentioned. So the background for this one was actually the NASA Ames test that we saw before. It was also the Mexico test, both wind tunnel tests where we had model rotors tested, and they were very good because everything was in control and we could test a lot of different things. What was not in the test was the actual size. It was the atmospheric inflow. It was the aeroelastic behavior of the turbine and so on. So Helge took the initiative to make this project in collaboration with Vestas and Siemens Gamesa, LM, and Ørsted. And you can see we were many involved in this project because if we really want to move and make a great effort, you also have to be many persons together to do it. So we selected a turbine just south of Esbjerg, and then we wanted to test on this turbine. And here you can see a blade specially made for this test. We have 4 different pressure rows covered with tape, and you can see Helge, Jonas Tromblad, and me standing there, and it was mounted on the Neckarmicron turbine back in 2009. Here you can see pitot tubes mounted on the blade, and you can see this special high-frequency inflow sensor also. And all this was then data that came from these tests. And they were analyzed in this International Energy Agency Task 29, and also now in Task 47. And now these data is just on a disk. It's a database, and you just go and take these data. But this is, you can say, before it will be data, then there's a lot of work behind this. And just to, I found actually a movie from just such a day in the test campaign, where it was so that we started out looking at the weather and say, in 2 days we have good weather, everything's good, we can test. We hire a lift, and then I went 5 o'clock in the morning to Esbjerg, and then I met the technicians 8 o'clock in the morning, and then we started out. And we started out by just unmounting tapes on the turbine and then starting you can say the measurement process. And they are then going by the lift up to the first section. I'll take it again. They went to the first section, unmounted the tape, and then they went again to the next section, and then finally we could start the campaign. As you can see in a moment, then we are running the turbine. But you can say such tests cannot be done without excellent technicians. So we have to really have excellent competencies all the way from, you can say, the super theoretical parts to the very practical parts. Otherwise, such things cannot be done. And results from this test, you can see here, this was, you can say, an investigation of the transition from laminar flow to turbulent flow. For those not familiar with this, at the bottom here, you can see a laminar flow where it's layered flow, and then suddenly at one point that we call the transition point, it turns to turbulent, and then the boundary layers will grow more. And because of this, the more to the leading edge we have the transition point, the bigger the drag will be, and the less efficient the airflow will be. So it's important to know where we have this transition point. And as you can see in these plots, black is laminar flow, gray is turbulent flow. Then this transition point actually moves around when the blade is either up or down. But even though we have this, then there will still be fluctuations. That will also is also because of turbulence in the air and so on. This is the lee side of the turbine. This is the wind side. So this is the pressure side, and this is the suction side. So this is very important, very unique. Even though it was unique at that time, I think it's still unique because it's so hard to do such measurements out there in the atmosphere on wind turbines. And then another plot that I just also want to mention here, because we investigated you can say, the energy in the flow, whether we were in a wind tunnel or we were out in the atmosphere. And if we went to the wind tunnel, we could measure the red curve, where we have the energy as a function of frequencies. And then we put up a turbulence grid to increase the turbulence in the tunnel, and then energy level increased as expected to this level. And then we measured in the atmosphere at the same position on the airfoil, and realized that between 500 Hertz and 5,000 Hertz, we actually had an agreement between the smooth flow in the wind tunnel without a grid and the atmosphere. And that is actually, these frequencies are very important for the transition behavior, where we transition from laminar to turbulent flow. And that is then a very important information, because then we could go for the polar cool tunnel and specify this and say, we really have to make low turbulence levels in the wind tunnel, because that is what the atmosphere will actually see. And that is why we had to make a very big wind tunnel, because we needed low turbulence. So this plot is super expensive, actually. Otherwise, we could have had maybe made a smaller tunnel. But that was very good. We had this plot. I will turn to rotor design, because I was responsible for this 10 megawatt reference wind turbine. And that started out in the light rotor project, again, together with many persons. And in this light rotor project, we wanted to make bigger rotors lighter, because we have to fight this square cube law, as we call it. So in this light rotor project, we want to have a starting point for the optimization, but we couldn't get a blade, so we had to make a blade. So we made this reference wind turbine, where we had aerodynamics and structural layup being absolutely consistent. So there was, you can say, the airfoils were consistent with the actual aerodynamics. So this was made to support such an optimization process. And the objective was to make it as a starting point, and then we also could test our tools, Hawk2, Hawk2, BCAS, Rotor, Ellipsis 2D, 3D, and so on, and establish an open source model. To the right here, very nice computations on the blade, and then we used this setup and this reference turbine to optimize it. And you can see an example over here where we have the short blades. This is seen from two different sides. The shorter ones are the D2 10 megawatt, and then we could actually increase the length and thereby the energy by optimizing it. So the D2 10 megawatt reference turbine is not an optimized turbine, it is just a turbine that was made in a sequential way, so we could get, you can say, just a transitional turbine made. And it was not only us actually that had the use of this. When I checked last week, we had more than 30,000 downloads of the description of the turbine. So that was nice that somebody out there could actually also use this turbine. I will go to the Polar Core tunnel now. The background for that one was that we tested in this Velux tunnel for many years, starting out in the start 90s, and this was actually our wind tunnel until 2007, where we made our last test. It was actually a good tunnel, but we had some issues because the velocities were so that we could only make tests corresponding to diameters between 20 and 40 meters, and in 2007 we were at 130 meters. So there was a bit of a gap there. We also had a turbulence intensity that was too high, and it was an open jet, so it required big corrections. So we simply just needed a bigger and better wind tunnel. And we did so. We actually got a project granted where we talked with the stakeholders in Denmark, the industry, the universities, the developers, and so on, all stakeholders. And we specified a test section that you can see, where you can see the specification here. And we also did it for, should do this for a fixed amount of money. So that actually, this is a challenge, you can say. And what do you do if you don't know how to build a wind tunnel? Because now I know, but I didn't know at that time. So we were kind of blank, even though we had many good people. So we should build this tunnel for this purpose. And then I tend to say at that time that we had to go in a Pac-Man mode, just eat one cheese at a time and get a solution to what about EU regulations, what about power to research, what about, and there was a lot of small things that we have to solve during this process. So that was fun. And you can say, I'll just turn to this. Drawings are very nice because you can always undo stuff. You can always go back and then change something and say, no, we don't want it like this. But when you drive in tons of concrete and steel, then there will not be no undo button. And if you had made an error, then it would stay there for 50 or 70 years or so. So that was both very rewarding to see it growing from the ground, but also a bit scary because we didn't know how it would work actually, to be frank. So such a one-off thing is interesting to build. And then we came to the first operation, and we had a sprint team working day and night up to this inauguration. Robert, me, Jimmy, Sigurd, Andreas, Anders, and that was fun and hard. And then also, you can say the first day we should switch on the fan. That was also very interesting because that was the time where we didn't know if the cooling circuits would break down or the guide vanes would stall or something did not happen the right way as we thought. So here we can see how
det godt, Jimmy. Ja, det er godt. 80 meter per sekund. Det er sådan der.
So this was very noisy because it was noisy, and that was very low tech to sit with a paper and a pen and a voltmeter and a piezo tube, but that was how it was at that time, and very efficient and very interesting. That was a very important day for us to see that it actually happened the right way, and it worked super nice. And we had this inauguration with His Royal Highness Prince Joachim. That was also a great day, and to show this nice facility to the rest of the world. And we continued after the inauguration, of course, because we had to instrument this wind tunnel with different configurations. We had the aerodynamic configuration, and then we had the aeroacoustic configuration. So the aerodynamic configuration has these, you can say, glasses and hard walls included. So we can actually test the aerodynamics at very high speeds. And then we have these Kevlar windows that can confine the flow, but where the noise can be emitted through the Kevlar and then be measured by the microphone array out here. So we actually obtained what we wanted. We obtained the high flow speeds up to and more than 105 meters per second. Check. We obtained the low turbulence intensity below 0.1%. Check. And also we obtained the low background noise that we had hoped for. Check. So that was very nice to experience this. And we had this project with the Aeroloop project with Vestas, Siemens Gamesa, LM and Suslan, where we had different activities. So we made aerodynamic benchmarks against other tunnels. It fitted very well to other tunnels. That was nice. We had aeroacoustic comparison also with Virginia Tech. That was nice. We had build up of a LiDAR in the wind tunnel. I would say that's work in progress. We had establishment of a measurement system from laminar to turbulent flow with, you can say, thermographic cameras where we can measure the transition line. We had dynamic a dynamic setup being built, so we could actually test, you could say, pitch movements of a blade. And then we had this digital twin where we can actually compute the flow in the wind tunnel. And that is actually super important because then we can investigate what's a lot of details in the tunnel that is hard to see in real life. So with the digital twin, we can see what's happening. And then we can also measure some things in the tunnel and go back to the computation and see, are we actually computing the right thing? So this interaction between measurements and computations, they are very important and have to be a continuous effort also in the future. And I've done a lot more. I've designed blades for smaller turbines. I investigated tip losses, double stall, trailing edge flaps. You can see trailing edge flaps there. Wind tunnel test of add-ons over there. Full-scale measurements also of rotor generators there. Erosion, a lot of measurements of erosion you can see up here in the wind tunnel, and then erosion safe mode where we reduce the velocity of the blades to save it for damages. Urban turbines, and then also this funny autonomous street lamp with both a wind turbine and a solar cell and more. So I have been somewhat around in my research. And now to teaching and dissemination and projects. Because in 2008, we were allowed to start out PhD projects because at that time we merged with DTU, and then we were actually allowed to educate PhD students. So it started at that time, and I've been main supervisor for these 6 PhD students. And there are, you can say, 3 themes in this. There are rotor aerodynamics, rotor design. That's where I work with Mads Døssing and Carlo Tibaldi and Kenneth Lundbæk. Then there is this urban wind energy that was a great project with Christina Bella. And then leading edge roughness or erosion, where I've worked with Emil Kruse and Tahir Malik, that's actually ongoing right now. So that's interesting, and that's also where you find out that okay, the PhD student is actually struggling with the rotor aerodynamics, and you realize that it is actually a super complex topic, and that this also push yourself to try to explain things, and then it also pushed me to try to explain it in its textbook, aerodynamic rotor design, and also aerodynamic airfoil design, and also teaching in master courses then kind of forced me to understand things better, and it's actually a challenge to explain what you know, but it's also a big privilege to do it. And actually then you also learn yourself, and just that's the fun fact, if you see a blade out there that is kind of curved, that is actually not an accident, that's actually on purpose, because the width of the blade, we call it the chord distribution, goes with 1 over r, and the twist goes with 1 over r also. So that is, when you study the equations, you find out, that's why. So you actually have this behavior, just so you know it. Projects. I put up this list of projects because I've been project manager for these projects. And this is just to say, research is not only measurements and analysis and computations. That is also project application, project ideas, and talking to people and finding out how to set up projects and new ideas and get it funded. And of course, it takes a lot of time, and you can choose to say, that's also annoying that we have to apply for projects, but I actually turn it around and say, it's actually a blessing that we have to talk to people and make a network, because you can see which companies and institutes I have been connected to, and there's a lot of knowledge out there, and there's a lot of knowledge that you didn't know was there. So you actually get in contact with things you didn't know about, simply just because you sometimes are forced into it. And that's actually what I also like about working with others than just internally. So this is also just important part of research. So to my vision, coming to an end, I have, before I want to just tell about this, I just want to find out what is actually happening in the close future. And if we study 10 years back, we have seen the biggest turbine developing like this. This is the red dots. And if you try to extrapolate this, then you will end up at radiuses of rotors between 150 and 180 meters. That's super big. You're ending up at 20, 30, 40 megawatts. So that's one thing that is probably to come. Another thing is also the knowledge that the industry is actually struggling with what I told you before about this square cube law, that things are getting relatively more heavy when you increase it in size. And we should actually believe that the mass of such blades increase with the length cubed to the third, but it is not. It seems that it is to the 2.2 or so. And that's because it's a conscious innovation in bringing down the mass. So there's a lot of innovation in this and pushing these blades to the limit all the time. So that's part of this. Then you can say, is this going to continue this size race? We don't know, but nothing is actually out there to show that it is not. But it's maybe not so efficient that it's just continues, because we cannot really optimize the turbines if you only have kinds of one edition of each turbine. But that's how it is. It's still running and upscaling in the future. Another thing is that we will have a massive installation of turbines, as it looks like right now. We have requirements such as power to X and floating foundation. So not only a massive installation, but also connecting to the remaining grid. And maybe there will also be, you can say, other branches of wind energy where we go to remote areas and put up turbines working, you can say, offline. You never know. Otherwise, we can support this also. So I have a vision for the design and performance of blades. Of course, we should try to maximize the energy for constant load. We should further make elastic design of rotors to include all the dynamics in this design process. We should investigate the loading of wind turbine rotors, such like peak shaving, unsteady loads, standstill loads. You can see peak shaving up here, where you just cut off the maximum thrust for the turbine, or standstill loads that VTOL was fighting with back in the old days. And then we should also balance between thick airfoils and mass and energy production. So we should try to find out what is the right balance between aerodynamic performance and structure. Design for X. So we should design for X. That means, yeah, we could design for power to X or sustainable materials or something else. So the turbine should be designed for its purpose. And then also we should try to go towards digital certification of blades. So we have a blade design here, and then we make it in real life. And then we have updated measurement methods where we pretty fast can get a very detailed description of the physical mechanisms, and then put it back and make precise models. So we actually can trust the models more and more and more. And in the end, hopefully, trust the digital versions of the turbines. Also, design of performance of airfoils. We should continue studying this 3D correction. You can see here how the flow is separated and how we should describe the flow in here. So that's 3D corrections. We should study high Mach numbers. You can see how the lift curve of an airfoil is actually changing, whether we have with the purple 70 meters per second or 140 meters per second. So this will actually change the forces whether you run with one or another wind speed, or you could say rotation speed. You should also study inflow and inflow turbulence. So if we have high turbulence, then we will have a much drag, and if we have low turbulence, we will have less drag. So that's super important also for the performance of the turbine. We have to understand roughness, such things like this. How will this actually influence the aerodynamics? Thick airfoils, high Reynolds numbers, of course, because when the blades are getting bigger, we get higher Reynolds numbers, so that we have to cover this somehow. And then aerodynamic and aeroacoustic add-ons, like these water stimulators, we have to also understand it even better. And not at least the polar core tunnel, we have to understand the flow in the test section better. We have to develop the test methods, update the, you can say, the acoustic measurements, not because they are bad, but they can be better. Visualization techniques like this PIV system with a laser sheet, the dynamic behavior of airfoils, we also have to investigate that. And then connect the tunnel to the rest. So we have, you can say, the polar core tunnel connected to, for instance, the rotating rig over here. You can see how that works. And then connecting this also to a full-scale rotor. So this about understanding what's going on in the wind tunnel to what's going on a rotor is super important. And that actually then is looking back to where I started, actually. Because at that time, I also had to understand why wind tunnel measurements did not fit to turbines. So even after 25 years, I'm back. But I'm probably spiraling like this, so the knowledge level increases, but I get back to the things to kind of refine it. So can I carry out this vision on my own? Of course not. I know that I have good colleagues and rely on very good collaboration, and that we can do things together and agree on very good projects. So I will strive after that my research has relevance and impact. And my vision will always support the D2 mission to develop and utilize science for the benefit of society. And it will also support the attempt to make life better in our personal box. So with this, I want to thank you. I want to thank you, my good colleagues in D2 Wind and Energy Systems. You can see a photo of my colleagues in D2 Wind Energy annual 2021 before we got PES division into the department. I also want to thank my good colleagues at other universities and in the industry, because that is super important to have good discussions with them. And not at least, I want to thank my good friends and my lovely family, because they are essential to me. So, thank you.